Well, what's up, everybody? We are back for question number 3 of the 2024 FRQ. So, this is the first one of the non calculator questions, and I'm excited to dive into it. It should be a pretty solid time. Looking like we got a differential equations question, which I find really, really fun. So, number 3, it says the depth of seawater at a location can be modeled by the function h that satisfies the differential equation dh dt equals 1 half times h minus 1 times the cosine of t over 2, where h of t is measured in feet and t is measured in hours afternoon, where t equals 0. It is known that h of 0 equals 4. So at t is equal to 0, at noon, the height of the seawater, or the depth of the seawater, is equal to 4 feet. Okay, so part A. It's going to be a little bit hard for me to show this on the screen, but it says a portion of the slope field for the differential equation is provided, and it asks us to sketch the solution curve, y equals h of t, through the point 0, comma 4. So obviously, I don't have the graph in front of me, but I can at least do my best to describe what a solution curve should look like for a differential equation. So these like random little dashes in the slope field, what they represent is the instantaneous rate of change of a function, that function represented by the differential, that passes through that point. So if we look at the point 0, comma 4, it looks like our slope is right about like 1, right? That looks like what our slope is equal to. So I would start off by drawing a solution curve that has a slope something like 1. And we see it slowly goes up and then it drops back down right around. This peak is around 3. It's not exactly at 3, but we have the point 0, we have the point 5. The peak of the curve is around 3, and that would be my sketch of the solution curve. All we do is try our best to follow the lines, and that will give us a solution curve. There are infinitely many solutions to a differential equation, but when we pass through a specific point, there is only one solution. So that is part A. Now, part B, I'm going to kind of do alongside part A, and we'll work through it together. And it says for t is between 0 and 5, it can be shown that h of t is greater than 1. So h of t being 1 is like somewhere down there. And that makes sense, right? Because our graph is entirely above that line. And it says find the value of t for t is between 0 and 5, at which h has a critical point. Determine whether the critical point corresponds to a relative minimum, a relative maximum, or neither. And it asks us to justify our answer. Okay, so we know that this curve is a graph of h of t, right? One very specific curve of h of t. And it asks us to see where there's a critical value. We know that critical values happen at relative extrema and places where our derivative is undefined. So looking at this, the critical value that I see is at this point right there. The one that we said was around 3, that is going to be our critical value, and it's going to be a relative maximum. But we don't know exactly what that point is. But we know that there is a horizontal tangent line at that point. So looking at our differential equation, it looks quite a bit complicated, but 1 half h minus 1 times the cosine t over 2, right? We know that at this point, our slope is equal to 0. So 0 has to equal 1 half times h minus 1 times the cosine of t over 2. Now they tell us that h of t is always greater than 1. So h of 0, or h minus 1, cannot equal 0. So what we are left with is solving for when the cosine of t over 2 is equal to 0. Now we know that cosine equals 0 at the top part of our unit circle and at the bottom of our unit circle. So we would get a value for t over 2. We would have pi over 2. We would have 3 pi over 2. We would have all of these values in the positive and negative direction. But they ask, we're looking for a value that's specifically like pretty close to 3, right? If I were to multiply all of these values by 2, I'll get that my t is pi, 3 pi, going on to infinity. Which one of these values is pretty close to 3? Pi. So t equals pi is our critical point. And it is a relative maximum because it is at the top of our graph of this function, or you could also say our function goes from increasing to decreasing at t is equal to pi. That would be fantastic as well. But that would be our correct answer to part C. So once again, just kind of using our knowledge of differential equations, knowing that this differential represents the slope at a point, and we were able to solve for the only way that that slope could equal 0 at this point. So an interesting question. I like it. But we're going to move on to part C. And part C is the finale that we see in a lot of differential equation questions because it says use separation of variables to find y equals h of t, the particular solution to the differential equation. And I'll rewrite it. It's the same one. dh dt equals 1/2 times h minus 1 times the cosine of t over 2 with the initial condition h of 0 equals 4. So to start out, using separation of variables, the way that we handle it is we get our dt to the other side, right? And we try and get all of the variables on the correct side. So I would want all my h's on the left side, all my t's on the right side. So in order to do that, I'm going to multiply by dt and then divide by h minus 1. So I get 1 over h minus 1 dh is equal to 1/2 cosine of t over 2 dt. So now I have separated my variables effectively, so I'm going to integrate both sides, do an indefinite integral. Now, one of the properties that we know with integrals is that the integral of 1 over x plus a is equal to the ln of x plus a. So because the derivative of this denominator, h minus 1, is equal to 1, we know that this left side will be the ln, the absolute value of h minus 1, and we will have a plus c. I like putting all my plus c's on the right side for differential equations. Now on this right side, I have 1/2 times the cosine of t over 2. So how are we going to do this? I personally would do a u substitution, and I will u sub my inner function, t over 2. That will get me du equals 1/2 dt, and this becomes the cosine of u. We have 1/2 dt, which is just the integral of the cosine of u du, which we know is equal to the sine of u plus c. I'll plug back in my t over 2 and get this as my final equation. The integral of cosine is equal to sine, so we get the sine not of u, but the sine of t over 2 plus c. And that is our solution curve. And this solution curve has infinitely many solutions because there's this constant, c. and it can be anything. But now we're going to use our initial condition. H of 0 is equal to 4. So when I plug it in, I get the ln of 4 minus 1 is equal to sine of 0 plus c. The sine of 0 is equal to 0, so c is equal to the ln of 3. So now we get the ln of h minus 1, the absolute value, is equal to the sine of t over 2 plus the ln of 3. Now, at this point, like this is an equation that represents this curve, right? We kind of would be at a stopping point, but the question specifically asks us to find y equals h of t, or to get h in terms of t. So I need to isolate h. To do that, we have this ln on the left side, and the tool that we use to get rid of the ln is we will do e to the power of both sides. On this left side, e and ln are inverses, so they'll cancel out. And I'll just get the absolute value of h minus 1 is e to the sine of t over 2 plus the ln of 3. Now, we know for this equation, h is always greater than 1. They told us that in part B. So h minus 1 will always be positive. So we can just kind of forget about the absolute value bars, add our 1 over to the other side, and get h is equal to e to the sine of t over 2 plus the ln of 3 plus 1. And this will be my equation, h of t, giving me my depth of the seawater in terms of my time, which represents the time after midnight that this is happening. Or not time after midnight, but time after noon. So that would be the whole of question 3 on the 2024 FRQ. I hope it was helpful. A really fantastic question going through some of the aspects of differential equations. But hope you guys have a fantastic day, and I see you soon. Happy practicing in some more calculus.